Okay, good day everyone. So, this is Thursday, April 15th, and tonight the the magnetism chapters assignment is due tonight. We're going to spend most of today looking at that, answering any questions you have about it. And then next week, the electricity and magnetism test will be administered by web assignment over the period of the week. So much like last time, you'll have a chance to, it'll open up to be taken on Tuesday. You'll be able to decide when during the week you just have the time and awakeness to take it. You can spend up to 5 hours once you start, send me questions, send me your work afterwards. And because a combination of that and Honors Day, no lab next week. So, additionally, unrelated, before we move on to anything else, remember when I was dropping magnets down this tube last week? I finally fixed it.
What was it?
Well, as with most things in physics, radius matters. And so I needed to be using bigger magnets that more thoroughly filled up the entire tube. So, these are all varying states of magnetic. One of them is just, actually two of them are just pieces of aluminum covered in rubber. So this is completely aluminum, no magnetic properties whatsoever. And it will drop in this amount of time. Pretty normal. Meanwhile, this one's a magnet. And again, aluminum, not magnetic. So nothing should happen here.
Oh, wow. Did you see it vibrate like that?
Hmm?
See it vibrate like at the bottom? It was like,
It's vibrating.
was it? Or was it me?
I mean, it could have been rattling back and forth a little bit. I wouldn't see that. That wouldn't be uncommon. I just don't think it's. I think it's just a problem of it physically sliding down, something that is just only barely wider than it. So, magnets are weird and they do several things we still don't completely understand. Because, again, the aluminum is not magnetic. It's only doing that because of the change in flux. That said, I have amended the homework and quiz somewhat. I've removed the flux questions from it because we didn't talk about that math too much. And I want to be fair to the other section. I haven't told them about flux at all yet just because of when everyone's having their classes. So, the assignment might look a little bit different, but I'm erring on the side of simplifying it for you guys as opposed to adding in newer, harder questions. So, tonight, the magnetism homework is due. And so, what questions do you guys have from this assignment or about anything we've covered so far in this particular chapter? Chapters magnets.
Number 6.
Homework 6. Homework number 6. Okay. It's a very good one to ask about. It's a very strange physical situation. So, in this particular question, we have two wires, both with electricity running through them. And when you run electricity through a wire, that wire will create a magnetic field, and that wire then becomes susceptible to other magnetic fields. So these two wires next to each other are both going to make fields that are going to exert forces upon the other wire. And we need to analyze the situation. First, are the currents in these wires in the same direction or in the opposite direction? This is just a concept question. When wires repel one another, and these two wires would have to be repelling for them to balance like they are on the strings, the current has to be moving in opposite directions. And I proceeds. Thank you. This visor is not great for sneezing in, because I have to decide, do I catch it or do I let it splatter against the mask? Terribly sorry.
My chemistry lab teacher lets it splatter.
Blech. I mean, besides being gross, it just makes it harder to see. Okay, so current in each would have to move in opposite directions for them to repel one another. We are told, though, each wire carries the same current I. So we are looking for one current with the same current in each wire. So whatever the I variable for each wire is, it should be the same. And that'll help us a little bit. Let's first erase math that is scary.
It's like a triple integral.
Yes. Welcome to physics with calculus. Sorry.
Do you teach that?
No. Not that I couldn't, it's just.
You like it?
Mm,
Do you like this more?
yeah, I just prefer algebra. It makes more sense to my brain. Not that calculus isn't important, not that I couldn't do it. But with my current rank and function at this school, my main priority, like my work function at this school is to handle the non-major classes so that the professors can handle the major classes. Okay. So the problem tells us two unparallel wires, each with a mass per unit length of. So.
I don't know what that means either.
And that's okay. I'm going to translate it for you. It means that, let's just assume we have a length of 1 meter for both wires. That means each wire should have a mass of 35 grams. Just to simplify it.
What do we like in this class? Grams or kilograms?
We prefer kilograms, so good observation. 0, 0.035 kilograms. So this would be the mass of 1 meter chunks of this wire. We're just going to use those numbers for the sake of our math. And these particular wires are being hung by 6 centimeter long strings. And it's a little, I know the resolution is a little fuzzy here, so to draw a different angle of the picture, just making sure that that angle distance is between the lines. It is. So everyone will have, as part of their question, 16 centimeters and 16 degrees between the two strings. some unknown current that is the same in both wires. Repel each other, so that yeah. So, we've already determined the current would have to be in opposite directions. And now we want to figure out the magnitude of the current that is traveling through each wire. They're the same current in each, just one number. So, what formulas should we recall? Yes, Ampere's law, also known as Biot-Savart law. So each wire is going to make a magnetic field. That field will be equal to permeability of free space. We'll rewrite that constant in a second. Times current over 2 pi r, r being the distance between the two wires. So that's another variable we don't know yet. And mu naught is 4 pi times 10 to the negative 7. So we know that one at least. So each wire is going to make a magnetic field that will subsequently affect the opposite wire. So we need the other formula that summarizes what kind of force we have. Oh, sorry, I didn't even show the last slide. We want the formula that now summarizes the force on a wire based on its current, the field it's exposed to, and its own length. So we can use this to find the field being produced. We can use this to find the force that field will exert upon either wire. So I'm going to write that one down too. We also don't currently know F.
Wait, why is length 1 meter?
So, within this formula, and I wrote it the same L because this is the variable that we're going to use it for. In this formula, the L represents the length of wire that is exposed to the magnetic field. And the problem tells us the mass per length of the wire, and if we just assume that 1 meter of each wire is within the other's magnetic field, then you can assume 1 meter for each. So it'll be the same whether we look at one wire or the other. And if we assume 1 meter length of wire, that tells us exactly what its mass should be, which will become relevant in a second because
For F?
for F, yes. My instinct when looking at this, and my instinct when looking at this is, what we ultimately want is I. And the two formulas we have listed that might be useful both contain I. In Ampere's law formula, we don't know B, we don't know R. We could reasonably find R, so that's not a concern, but we don't know B yet. In the second formula, we have current, but we don't know F and we don't know B still.
I think we find F, and then we solve in each formula for I, and then we set them equal to each other and find B. Can you do that?
We can do that. Alternatively, we can solve each formula for B and set them equal to each other so that we find I instead.
Oh, so it's just faster. Wait, but what about F?
So yes, we do need to figure out F. In order to use this formula, and if we then combine the two, either To use this formula, we're going to need F, because the other formula, we can't do any substitution tricks to get rid of F yet. Which means we instead need to look at the physical situation that's going on here. These wires are being repelled from each other by some force. And that force is what is currently keeping them apart and what is keeping them both from falling all the way down this corner they can go. So, quick 1500 review. What would all the forces on this wire be?
Tension,
Okay?
force of gravity,
Okay?
and then probably force of magnetic field to the left, right?
Correct. Call that B field, B force. So there's three forces acting on this wire, and we can do a little bit of force analysis, a little bit of trig to figure out what the force acting on the wire is.
So you only solve for one, because like the other one's the same, just like different signs.
Correct. We're assuming both sides to be equivalent, just pointing in opposite directions. We are told the current on either side is the same. They're both repelling the same amount from their origin. They both have the same mass per length, so the force of gravity on each of them should be the same. So yes, we're assuming just complete lateral symmetry. Which means we only need to really look at one of them to start with. So, out of all these forces, the one we want most is FB, because that's the force that is currently in the other formula.
Oh, it's FB, but FB is not B.
It's not the B field, it's the force the B field is exerting.
Oh, wait, that is FB. Really?
Really. Because this is the force exerted by the magnetic field on wire with current in it. So this is a magnetic force. This is the force that is causing the two to repulse from one another. And so that is the piece of information you most want out of this whole bit here. And I'm going to do a little bit of creative license and redraw this triangle. Using a little bit of my trig knowledge to skip a few steps. Because all the forces on this particular wire, and we're looking at this wire from an odd perspective, the wire would be coming out of the board right now. Because all the forces on it must add up to 0 for it to be hanging still in the air, all of the forces on it must add up to 0, and if you were to add every side of a right triangle together, they all come back to 0. Like follow this path, this path, this path, we come back to the same point. So all of the vectors form a right triangle if you draw them this way. The scale might be a little bit off, but all the sides are in the right place. So we can do some trig to help skip a few steps. So, that topmost angle is actually going to be half of that 16 degrees. So this will be 8 degrees.
Oh, that's why it's a right triangle.
Yep. So just looking at one wire at a time, this is the tension in the one string, the force of gravity acting on this one wire, and then the magnetic force pushing on this one wire. I've just taken all of these vectors and rearranged them into a right triangle. And we know one angle So all we need to figure out the other sides is one of the sides. We were told the mass, so we can find its weight.
Really? We can find FG.
Yes. We know its mass, so Fg equals m times g. We already converted mass to kilograms, so we multiply that by 9.8. That should be like 0.3 something. Where does my calculator live? Very long.
0.343.
Say that one more time.
0.343.
Thank you. This is a force, so that's in newtons. That is the weight of the wire, and that forms the vertical leg of the triangle, whereas magnetic force forms the horizontal leg. So we know one side, we know one angle. Trig can get us the rest of the way there. It saves us having to do all of the dividing up into vectors and adding
Opposite.
calculating.
Tan.
Yes, so tangent of this angle equals opposite over adjacent. Saves us from having to solve for the hypotenuse. Tangent of 8 degrees will equal opposite over adjacent. That's going to be f b over 343. How do you guys feel about this method? If I'm going too fast, please, or if this is just a strange way of doing it for you, please let me know.
I just didn't know that it was the same force. I guess I didn't think about that being the magnetic force. So
Yes.
like, I tried to I was confused on how I would find that.
That's fair. It's a physically weird situation. You've probably had things repulsed because of electric force, but who's ever set up two wires and turned on the current and watched them move away from each other? At least not wires with current in them.
At 0.048.
Wait. Can you repeat what you got?
0.0482.
Okay. My brain definitely stopped working for a second there, sorry. So that's our magnetic force. And that force will be acting with the same magnitude on either wire.
This is so much more, I don't like that drawing at all.
Yeah, that's fair.
And what was the point of the 6 centimeters? Oh.
It will become relevant in a second. Just one piece at a time. We now know our force. Let's start plugging a few things into this formula. 0.0482 equals I times B times L. We're using 1 for L with the mass that we've used. So, now we need to approximate what B is. We have a formula for B. This would be the field produced by one wire, and that would be the field acting on the other wire. They both have the same current running through them, and they're both the same distance apart, so they should both be creating the same amount of field that will be affecting the other wire. So again, perspective of which wire we're looking at is not really important right now, but we can take this and swap it into here. Taking that formula and plugging it in for B, we know this constant, this is the same I, so that just means we're going to end up with an I squared. The last thing we don't technically know yet is R. So The length of the string is now going to become relevant because we need to do trig again to figure out how far apart the wires are at this point. So, I'm going to take this same triangle and make a distance triangle out of it.
Oh, that's where you need the 6.
Yep. Call this side, bless you by the way. I'm going to call this bottom side R over 2 because this is half the distance between the two wires, technically speaking. The full distance would be the bottom sides of the 2 right triangles that we formed here. So this, if we just do trig with the 8 degrees, we're only going to get half of that value. That said, I'm sure there is a formula for finding the last side of an isosceles triangle. I just don't know what it is off the top of my head.
That sounds fun. So we do sine.
Sine this equals opposite over hypotenuse. So that will be R over 2 over 6. That will tell us that the side of the triangle will be, if I had to guess, around 1 centimeter maybe, or less.
It's 0.83, but then when you divide it by 2, it would be 0.4.
Ooh. I got 1.67.
So everyone make sure your calculator's in degrees mode.
Not for
just
R
in
over
case.
2. For R. So
For R over 2 at 0.85 centimeters.
That's what I thought.
That means that R would be,
0.4
it'd actually be 1.67.
Oh, I did get that. For R.
So we
Wait,
need
going
to-
by 2?
We need to multiply both sides by 2 to get R by itself.
Okay, yeah.
1.67. That's R.
That's R. That is R in centimeters. Be mindful of that.
So meters.
So 0.167. Sorry, 0.0167. But we know what permeability constant is. I is the only thing left. We can find it now. And I will do that with these numbers to prove this whole thing works.
Wait, so we said I was 4.5 centimeters.
Where did your 0.167 go?
Oh, that's my problem. I just forgot to write it. Thank you. That explains why I'm not getting the right answer. Thank you very much. Much better. Yes. So I'm getting a grand total of 63.4 amps, which, again, review, will kill a person maybe 200 times over. So I don't know who set this thing up or why.
Wait, is there a decimal? There? Yeah, right.
Yeah, that's a point for.
was tricky.
Yes, so I'm glad you asked. Now, everyone will have a different, actually, I think the only variable that will differ between everyone is the mass.
Yeah, so it's just that left part, the 0.04.
Right. Because, yeah, the triangle's the same, so the radius will be the same. All that will differ is mass, force of gravity, and then E fields. Mag force, magnetic field force, that's what's different. Questions about this one?
So could you go ahead and divide those two numbers on the right and then you would divide them both to the left?
Yes, if I was to show more steps, I would,
Multiply by reciprocal. Right?
yes.
Or you could.
Well, okay. The way my brain works, I see 4 pi divided by 2 pi, and I think simplify.
Oh,
So, yes, we can multiply by the reciprocal. That would give us 0.0167 over 2 times 10 to the negative 7 times 0.0482 equals I squared. Whatever that is, we need to take the square root of both sides.
Can we just 7?
Yes. Okay, yes, absolutely. First, any other questions about 6? Okay. After later, please ask.
just really quickly. Is there a formula that relates electric field to velocity?
Electric.
Or, wait, did I say that right? Yeah,
There's one that relates magnetic field to velocity.
and then you're supposed to like, okay. That's
Might.
what we decided.
I don't want to be thinking of. You might be thinking of magnetic force acting on a charged particle in a magnetic field. Now, for number 7, a loop of wire, a single turn loop of wire. So again, this one might be visually confusing because they didn't include a picture. Sorry about that. Pictures are needed on the test. I will try to include them myself in the instructions. This single turn loop of square loop of wire would look something like this. 3 centimeters on the side. We're considering it to be a square, so each side is 3 centimeters with these numbers. Carries a counterclockwise current of 3 amps. So counterclockwise means the current will move like so on each side. Loop is inside a solenoid with the plane of the loop being perpendicular to the magnetic. Oh no. Wait, no. Okay. Okay, so this square loop is inside of an object called a solenoid, and we've actually worked with solenoids before, a solenoid. This is a slide in the notes. Technically, any coil of wire can be considered a solenoid. It's just a coil that you run electric current through, and when you run current through it, it will create a magnetic field of a particular shape, primarily inside of the solenoid. So when we made generators and electromagnets the other week, that weird copper coil that we connected with everything else is technically a solenoid. It's just more donut shaped than tube shaped. And what the question asks us, and I'm going to come back to this picture in a second. The question is asking us, is telling us that this solenoid is going to exert a magnetic field, and that field is going to exert magnetic force upon this loop of wire. So we know F equals I/L. Magnetic field is going to exert force on each of the wire lengths with current in them. And for this particular situation, we know the length of each wire and the current in each wire. That's that 0.3 amps on the screen. Your numbers will vary. So we know all of the currents and we know all of the L's, we just need to know the magnetic force that this particular object is being exposed to. So the magnetic field this object is being exposed to in order to find all of the forces acting on it. So we're going to need to figure out the field produced by this solenoid. And there is one formula that does just that.
What's R?
That is the radius of the tube of wires. So this distance. Hopefully. As long as 20 turns per centimeter. I don't like this question. It's more complicated than I realized at first.
Is the 20 the end?
Yes, it is. Except, okay, this problem is even more deceptively tricky than it seems originally. And I apologize. It's not my intention in the slightest. I'm sorry. So like, the physical situation is this square loop that we've drawn has to physically fit inside of this coil. And it doesn't really tell us how big the coil is. It tells us how many loops it has per centimeter of coil. And in order for this square loop to fit inside the solenoid, it has to be 3 centimeters long
Square loop. Wait,
and 3 centimeters wide.
this is square. Right, like the same.
Okay. There's too many steps here and too little information given for my own comfort level, because if I can't look at it and immediately tell exactly what needs to be done, it's not fair for you guys. So I'm glad you asked about 7. I apologize for 7. I'm going to be replacing it with a question about the same type of thing, but that doesn't require you to do 8 million tons of guesswork about a solenoid.
So will we be given more information so we can easily do it?
Yes, absolutely. If I was, I'm going to make sure that all the test questions are like that. So, if the WebAssign questions don't give you the information, I will make sure that that information is given out via instructions that I send out next week, including some hand-drawn pictures if needed. But the way 7 is worded, if it takes me too long to figure it out, it takes me more than a minute, it's not fair for you guys. This could be done, I just don't know.
Would the forces still be the same on opposite side?
Yes, because every wire has the same current in it and it's being exposed to the same magnetic field and they're all the same length, the forces on each part of the loop would all be the same. And if you put it in wrong, those forces would all cancel out and it wouldn't end up spinning. So you have to make sure it is in the correct axis so that the forces create torques and it actually starts rotating. That was what the second part was about. Okay. These are my own question that doesn't have some bits. Okay, we're at the end of the period, so I'm going to be revising that question. There will be I am intending for a replacement question to be there that is about the same type of situation, the loop inside of a magnetic field that is the function, the primary purpose, and the logistical source of operations for motors/generators. The formula involved for that should be involved there is this one. Again, the box is the only part you care about. This is just the formula for torque acting on a loop inside a magnetic field with a certain area and current running through it. The old box part is the only part you actually have to use. So there will be a similar question about a loop inside a magnetic field that will hopefully end up spinning. I apologize for the solenoid bit. That will happen about shortly. It's the end of the period. Does anyone have any questions before we finish for today?
Will it still be here tonight?
I might change it tomorrow, just for fairness sake. Speaking of tomorrow, I'm also going to be posting shortly some study questions and a list of topics to study for the test. And you can, again, that will be able to be taken at your leisure next week. During class next week, unless you guys have practice questions, I'm going to start talking a bit about light and sound, just as the last couple of things to talk about, because they're important to know, and it'll be something that we can do during the day that shouldn't distract you too much from the test you might have later. So, you have a good day. Please let me know if you have any questions, any issues with the assignments. That the new replacement question 7 will be out soon. And thank you all. Have a wonderful day.
Can I ask you about 5?
You can. You just,